So now we discuss the types of collisions. So in the type of collision, as we discussed, that if the external force is zero, the momentum change in momentum will be zero. So here we will just consider the system in which the external forces are zero. So we don't talk about the momentum because we know that the momentum will always be conserved. So before the collision or before the interaction and after the interaction of the particles, the momentum of the system will be conserved. So here we will talk about the kinetic energies. So if we have two particles, if they collide with each other, so this means that the momentum or the velocities will be changed. There will be a change in the velocities. If there is a change in the velocity, that means that the kinetic energy will be changed. So we write the kinetic energy plus a term Q equals kinetic energy. So this is the after momentum, after the collision. So this is the kinetic energy before the collision, and then we have the term Q term. We will just discuss this term, and this is the kinetic energy after the collision. So if this term Q, the term Q is larger than zero, it means that the system gained energy, the kinetic energy. The kinetic energy after the collision is higher than before the collision. It means that the kinetic energy is increased. So for example, this type of collision is called the super elastic collision. So this is the super elastic collision. So example of this type of collisions or this type of interaction is the explosive materials, because initially the system will be, for example, we have a explosive material. So before the collision, the velocity is zero. So which means that the velocity is zero, the kinetic energy is zero. But after the explosion, which is the interaction, all the particles will move, so there will be a change in the velocities, and these particles will gain velocity, and in other words we can say that the kinetic energy of the system will increase. If the kinetic energy of the system is increased, this type of collision is called as the super elastic collision. So the explosive example of the explosive materials or the momentum of the explosive material we will discuss later in this lecture. So if the term Q is zero, so this term, if the term Q here is zero, it means that the kinetic energy of a system before the collision and after the collision, they are the same. If they are the same, this type of collision is called as the elastic collision. Elastic collision. So the example for this one is if we have the perfect ball, for example, if we throw a ball on a floor or on a wall, so the ball will have some initial velocity, and when it hits the wall, it will come back with the same velocity. So it means that the kinetic energy is not changed. So this type of collision is called as the elastic collision. And the third type of the collision, when the term Q is smaller than zero. And when it is smaller than zero, it means that the system lost some energy. So in the example for this one is that if you drop an egg on the floor, for example, if you drop an egg on the floor, it means that the velocity of the egg after it hits the ground, the kinetic energy will be converted to other forms of energy, so the system loses the kinetic energy. Of course, the momentum will be conserved. And this type of collision is called as inelastic collision. Inelastic collision. One thing we have to understand, that the change in the kinetic energy does not mean that the energy is not conserved. Energy of the system is always conserved. In the case of explosive material, the system gained kinetic energy, and this kinetic energy came from the chemical energy that was stored in the system. In the case of the elastic collision, means that there was no change in momentum. Change in the kinetic energy means the system did not gain the kinetic energy, nor it loses the kinetic energy. In the case of the inelastic collision, so this is inelastic collision, so the system loses kinetic energy. For example, if you drop an egg on the floor, so this kinetic energy will be converted to other forms of energy. It will produce a sound, for example, and also the egg will break. So this energy will be consumed in the breaking of the egg. So this energy can be converted to sound energy, can be converted to mechanical energy, can be converted to light energy. So the total energy is conserved, but we are talking about here only the kinetic energy. So the total energy of the system will always be conserved, but here we talk about the kinetic energy. And now we will discuss some examples in which we will try to understand the inelastic collisions, and we will also understand the super-elastic collisions. So for the elastic collisions, it's easy to understand when we throw a ball. So before we calculate the kinetic energy before and after, they will be the same. But to understand the inelastic collisions, in which the kinetic energy will be changed, and also the super-elastic collision, the kinetic energy is also changed. So we will discuss some examples in which we will try to understand this type of collisions here. So we have two objects, for example. They are moving with different velocities, and after the collisions, they stick together. So for example, we have object 1. So this is the M1, and it is moving with velocity V1, and we have the M2, and it has the velocity V2. So the velocity of V1 is higher than V2, so after some time they will collide with each other, but after the collision they will stick together. For example, there is some glue or something, or there are magnets, for example, they will stick together. So we will have the M1 and M2, M1 and M2, so they are plus. Now this is now one system, and they will move with V prime. So we don't write V1 or V2 because they are moving together with the same velocity. So before the collisions, they were moving with a different velocity, and after collision they just stick together and they are moving with the same velocity. So we can also say that the V1 prime, so after the collision, is equal to V2 prime, and we have the V prime. So we just write that, so they are all equal. So because they are sticking together with each other, so they are moving with the same velocity, so we don't have to worry about these prefixes here. So here the total momentum of the system before the collision, so before the collision here, so we can write that it is the M1 V1 plus M2 V2, and after the collision, since they are sticking together, so we have the M1 plus M2, and they are both moving with the V prime here. So this is the initial momentum, means momentum before the collision, and this is after the collision. So after they interact with each other, this is the momentum. So the velocities here, so this is velocities, it is a vector. And now we will discuss, we will take some examples. So we have the example 1. in which they are moving in the same direction but with the different velocities. So we have, for example, the mass m1 is equal to 1 kilogram, and v1, the velocity before collision, is 5 meters per second, and m2 is equal to 2 kilograms, and v2 is equal to 3 meters per second. So what we see here, that the v1 has the higher velocity than v2. So they will, after some time, they will collide with each other, but after collision they will stick together. So they will stick together and move with the same velocity. So according to the conservation of momentum, so the momentum before the collision and after collision must be equal. So we write the statement which we just discussed in the previous example. So momentum before the collision, so this is the before collision and this is the after collision, they must be equal according to the conservation of momentum. v1 plus m2, and this is m prime, v prime. So this is, if you put these values here, so if you put these values, so we will get 11 here on this side, and on this side we will get 3 prime, v prime, or we can say that v prime is equal to 11 by 3. So now we know we have the mass of the object 1 and mass of the object 2. We have the velocities, and also we have the masses, so masses will remain the same. So we also have now the velocity after the collision, and now we calculate the kinetic energy. So kinetic energy, so this is before collision. So before collision we have the m1, 1 over 2 m1 v1 squared plus 1 by 2 m2 v2 squared. If we put these values, so we will get 21.5 joules. So this is the 21.5 is the kinetic energy of the system before the collision, or before they interact with each other. So now we calculate the collision after the kinetic energy after the collision. So after the collision we have the 1 over 2, but they are sticking together, so m1 plus m2. So we have all the values. We have the mass 1, mass 2, and we also have this prime velocity, which is v prime, and this squared. If we put all these values, so we will get 20.2 joules. So what we see here is that the before collision, the system has the total system. So this is the particle 1 kinetic energy, the particle 2 kinetic energy, and the total kinetic energy was 21.5 joules. But after the collision, the kinetic energy, we can clearly see it is reduced. So this kinetic energy is reduced and it is converted to some other forms of energy. So it might be the sound energy or heat energy, but here the kinetic energy is reduced, so we can say that this is the inelastic collision. Moving in the same direction, and now we take the example in which they are moving in the opposite direction. So one is moving in this way and other is moving in the opposite way. But the masses, we take the same masses there. So now they are just moving with the opposite direction. So m1, this is m1, this is m2, and this is m2. 2, so they move with the opposite direction, and after the collision they stick together. So we have the same velocities, same masses, but now they are moving in opposite direction. So we have the first one has the velocity so we have the 5 V1 is still the 5 meters per second, 5 meters per second, and V2 has the velocity of 3 meters per second, but now they are in opposite direction. And now we want to calculate the kinetic energy before and after the collision. So if we calculate the momentum of the particle 1, so particle 1 has the momentum, if we put those values, so we will get 5 kilograms meters per second, and for the particle 2 we will get -6, because minus sign is telling us that they are moving in opposite direction. So -6 means the velocity there, velocity here is 3 meters per second and the mass is 2 meters per second, so mass velocity we have the 6, but since it is moving in opposite direction, so we have the minus sign there. So kg meters per second, and here 5 means the mass is 1 kg and the velocity is 5 kg, so 1 multiplied by 5 is 5 kilograms, so this is the kilogram meters per second. And now if we calculate the V prime, so we will get 1 by 3. And now since we have the values, if we calculate the kinetic energy in this case using the same equations here, so now we have the V prime, so we have the V prime, we have all the values here. If we calculate the kinetic energy, so so this is before the collision, so before the collision we calculated it was 21.5 joules. So we have the 21.5 joules, and after the collision, if you use this prime, V prime here, so after the collision, Ke, so this is the after collision, so we will get 0.17 joules. So what we see here in this case, when they were moving in the same direction, we had a very small change in the kinetic energy, but now we can see that they are moving in the opposite direction, and there is a huge change in the kinetic energy. So this is the kinetic energy of the system. The kinetic energy of the system before the collision is 21.5 joules, and after the collision is 0.1 joules. So the kinetic energy is definitely changed here, so it is the inelastic collision. So we just discussed the example in which the kinetic energy of the system before the collision and after the collision was different. In fact, it was reduced, so it was the inelastic collision. And now we just take the example of the real example. For example, we have a car. So we have a car here. It's moving in this direction, and we have another car which is moving in this direction. And when they collide with each other, so the velocity of this one and velocity of this one will definitely change. So the velocity after the collision, when they collide with each other, will be almost zero. So we will get so they will destroy, so there will be just after the collision or accident, they will just destroy, the cars will be heavily damaged. and the velocities will be 0. So what we see here, so this car or this object had the velocity, means that it had the kinetic energy, and this had the kinetic energy. So before the collision, the kinetic energy of the system was definitely more than 0. So and after the collision, when they collide, so after the collision, the kinetic energy is 0. So the momentum is conserved, but the kinetic energy is not conserved here, and that kinetic energy is converted to other forms of energy. First of all, it will produce a loud sound, so that kinetic energy is converted to a sound. And also there is a heavy damage on the car, so the car will be heavily damaged, so the window glasses will be broken and the car itself will be damaged. So this kinetic energy is also converted to this mechanical energy, and also this will produce a heat. So its kinetic energy will be converted to heat, and if it's moving with really high speed, it will also produce some light. So this is the real example of the inelastic collision. Another example is if you drop an egg, for example. So if you drop an egg, so the egg will have some velocity, and after it hits the ground, so the kinetic energy will be converted to sound energy and other forms of energy. So that's another example of the inelastic collision. So now we discuss the 2D system. So everything we discussed was mainly in the 1D, one dimension, and now we discuss the 2-dimension system. For example, we have a mass M, which is moving with velocity vi, and it has, so we have the M2 here, and it is moving with the velocity v2, and after some time, so this particle M1 has the momentum of M1, so P1, and this one has a momentum, so this has the momentum which is higher, and this has the momentum which is little bit lower. So the particle here is moving in this direction with the velocity, and also the particle 2 is moving in this direction. So in the different direction, we have a 2D system here. So they have a momentum here, and after the collision, the total momentum will be the sum of, so we can, since the momentum is a vector, so we can use the parallelogram method, and this will be the momentum. So this is the net momentum of the system. So after the collision, so the net momentum is in this direction. And now we discuss the example of the superelastic collision. In the superelastic collision means the kinetic energy after the collision is higher than before. So we have the explosion. So here we have, so we have a big mass. So this is the mass is, we write with the capital M, and it has the velocity which is 0. So the velocity of this mass is 0. So this is the explosive material, and after the interaction or after the explosion, so this mass, so this after the explosion, so this is, for example, is split into 2. So this is M1 V prime here, and this is the M2, and this will move in the opposite direction. So this is V2 prime. So what we see here in this case, so the kinetic energy is definitely higher than before, because the velocity here is 0, and after the explosion, so this will, the kinetic energy is higher, but the momentum is conserved. Since they are moving in the opposite direction, so the momentum of the system will be 0. So before, according to the conservation of momentum, since the velocity here is 0, as we can clearly see, so since the velocity is 0, so before the total moment, so before the collision, so we have the 0 momentum. So momentum here is 0. So after the collision, so we will have m2 v2 minus m1, so this is v2, means that m1 so they will cancel each other. So the total momentum is still conserved. So before the collision, the momentum was 0, and after the collision, the total momentum is 0. Of course, the total momentum of this particle is not 0, and this particle is not 0, so the individual particle's momentum is not 0 after the collision, but the net momentum is 0. And this force, the force that is produced because of the chemical energy, and this force is the internal force. This is not the external force. So that's why the momentum is still conserved. So this is the example of the super-elastic collision. And now we discuss an example in which two particles with some masses will also have some velocities, and they collide, and we want to know what's actually happening to the velocities of those particles. So it all depends on the velocities of the initial particles, means before the collision, and also with the masses. So we will just discuss 1D examples. So they are moving in the one direction. So we have the one-dimensional example. So we have a mass m here, and it is moving with the velocity v1, and we have the m2, and its velocity is 0. So what we see here, so we have, this is the m1, so this m1 is moving with the velocity v1, and it's moving towards the v2 m2, and it collides with the with the m2, and we want to know what is happening to the velocities of the individual particles after the collision. So in the previous examples, we were mainly discussing, or we were concentrating on the kinetic energies and the momentums, and now we want to see what's happening to the velocities. So after the collision, so this is the before collision. So after collision, so we have the m1 here, and so it can either go in this direction or come back. It all depends on the mass of the mass and the velocity of the m2, and also this one. So we will discuss in which direction they are moving. So this is v1 prime, and this prime, this dash, is telling us about the velocity after the collision. And m2, since it was initially at rest and the velocity was 0, so this will either be the velocity will be 0, or it will be the direction of the v1. It cannot come in this direction. So because the initial velocity was 0. So this is v dash. So now the conservation of momentum, so we have the m1 v1, so this is, we have the m1 v1 plus 0, because the momentum of the second particle is 0, because the velocity was initially 0. So we have the m1 v1 prime, means after the collision momentum, and then we have the m2 v2 prime. So this is the equation number, for example, A. And now we write the same equation for the kinetic energy, so before and after the collision. So we have the 1/2 m1 v1 squared plus 0 again, because the velocity is 0. So here we have the 1 over 2 m1 v1 prime squared plus 1 over 2 m2 v2 prime squared, and this is our equation number 2. So what we want to know, that what is this, the velocity of the particle after the collision and the velocity of this particle after the collision. So if we calculate, so I will not do the calculations because it's taking time, but I will just write the final result, and also I will discuss what's actually happening there. So V1 equals m1 minus m2 m1 plus m2, so V1, and V2 equals 2m divided by m1 plus m2, and also there is a factor V1. So now we have these two results, and now we want to see what will happen to the velocities if we change the masses of the particles. Right now, the velocities, we know that the velocity of the initial particle is, the second particle is initially 0, and the second one was had the non-zero, the first particle had the non-zero velocity, and the second particle had the zero velocity before the collision. And after the collision, we will see what happens when these two particles have different masses. So we have the case 1. So in the case 1, when the mass of the m1 is much larger than m2, if we put these values, it means that the m2 is almost 0. So it's the mass of the m2, the particle, the m2 is at rest initially. So the mass of the m2 is almost 0, which means that the mass of the m2 is so small that it's negligibly small compared to m1. So what will happen to the velocity m1, v1? So we have the v1 prime, and if we put the values there, so it will be equal to initial velocity. So the final, after the velocity of the m1 particle after the collision will be the velocity before the collision, because we can see here, we can clearly understand that so this particle was the mass is extremely small. It's like extremely small particle, and when this particle hits this mass, since the mass is so large, so this particle will not even feel this particle, and it will move. So this particle will move with the same velocity, and the velocity will not be changed. So this is what we see here, and the m2 velocity, v2 velocity will be equal to plus 2v1 here. So what we see here, so nothing will happen to the velocity of m1 because this mass is so large, but this particle will move in the same direction with the velocity which will be equal to 2 times the velocity of v1. So here, so this velocity. So here we have the example of the first case where the mass 1 is much larger than m2, and when the mass 1 hits the m2, the velocity of the m1 is not affected. Just look at it, and the velocity of the m2 is much higher than the m1, which is like 2 times the velocity of v1 we just calculated. So in the case 2, when we have the M1 is much smaller than M2, which means that here the M1 is almost 0. So in this case, the mass of the M1 is extremely small compared to M2. So what will happen? So M2, since the M2 is at rest, so if you put these values there, means the M1 is 0, and we put the M2 a non-zero. So what will happen? Well, after the collision, this will have the same magnitude V1, but it will just come back because the M2 is at 0, and M2, since M2 is much larger here, so the M2 will not even feel this M1 anyways, so it will remain at rest. So in this case, when M1 is much smaller than M2, the V2 velocity is not even affected after the collision, and V1 will have the same velocity, and it will come back to its original position, and the M2 will not be even affected. Case 3. So when M1 is equal to M2, so when M1 is equal to M2, so if we put these values there, it means that this 2 is 0. If M1 is equal to M2, so this term is 0, for example, and we do the same calculations there. So what will happen, the final result that we will get is that the V1 will be 0 and V2 prime will be equal to V1. So what we see here, so the particle M1 was initially moving with the initial velocity, and when it hits the second particle, which was at rest before the collision, so this particle will stop and its velocity after the collision will be 0, and the kinetic energy or the velocity will be completely transferred to the particle 2, M2, and this particle will move with the same velocity. And now we discuss an example in which we will use the concept of the conservation of momentum, and we will try to apply it. So it will be kind of the application of the conservation of momentum. So right now, today, we have very sensitive objects, sensitive instruments to measure the speed of a bullet. So very fast objects, we can measure the speed of the bullets. But for example, 100 or 200 years ago, we did not have these high sensitive objects or sensitive instruments to measure the speed of an object. For example, right now, if we want to measure the speed of a bullet, so what we have to do, we just have to measure the distance that it travels, and we just start a timer, for example, how long does it take, for example. But the speed of the bullet is extremely high, so how do we measure the speed of the bullet if we do not have these very sensitive instruments? And this instrument that was used before the modern era is called the ballistic pendulum. So it's called the ballistic pendulum. So we see here, we have a pendulum here. So it has the pendulum. So we have the pendulum which is attached to, for example, a roof, and we have a very heavy object. So we have a heavy object here. This is the center of the mass of the heavy object, and the mass of the string here is relatively very small compared to the mass of the object here. So this object here is a kind of, we can say, a rubber, and its mass is a capital, we can represent this with a capital M. And the length here, so this length from the center of the mass is 1 meter. And we have this initially, the velocity or this pendulum is not moving, so the velocity or the movement of the pendulum is 0. And we have a fast moving bullet, and its mass is small m. We represent it with a small m, and the bullet is moving with the extremely high speed. So initially, this is the speed, and initially the speed of the big mass is 0, but after it hits the pendulum, when the bullet hits the pendulum, and the bullet will penetrate this pendulum or this object, it will stick inside here. So we have a bullet which is inside, and the kinetic energy of the bullet will be transferred to the pendulum. So when the kinetic energy is transferred to the pendulum will move from its original position. It will start moving. So, and now at the maximum height, at the maximum amplitude, all these the kinetic energy is converted to the potential, gravitational potential energy. And now what we see here, so this is the center of the mass here, and we have the center of the mass which is now here. So this distance is called the h, and this distance here, we represent this one. So the center of the mass moved from here to here, so this is x. So initially the bullet had the kinetic energy, and the kinetic energy is completely transferred to the pendulum, and after some time the pendulum will start its movement, and after some time it will stop and will come back. But at the maximum position here, which is the maximum amplitude, all that kinetic energy is converted, all the kinetic energy of the bullet is converted to the potential, gravitational potential energy. So we can use the concept of the conservation of momentum. So the mv, so this is the momentum of the bullet plus 0, because the momentum of this pendulum is initially 0. So this is before, the momentum before must be equal to the momentum after the collision. So we have the big M, because they are the same, I can write it here. So they are now, because the bullet, the M is sticking in the big M here, which is inside. So we have this is the final, or the velocity of the system after the collision. And if we know this velocity, which is after the collision, then we can easily calculate the velocity of the bullet. So how do we do that? So this is the conservation of momentum, but from this we know that the total kinetic energy is transferred to the gravitational potential energy. So we can write the gravitational, or the conservation of energy. So we have the 1/2 m, big M plus big M squared equals m, big M, g, h. So the kinetic energy here, we can see here, this is the kinetic energy of the system. This is completely transferred to the gravitational kinetic energy. So this is the m, g, h. So this is the kinetic energy. So these two cancels, and then we get the relation. Here we will have the 2gh. So what we see here, we have the G is known, we have the 9.8 meters per second squared, and if we know that H, if we calculate the H, then we can easily measure or calculate the final velocity, and using the final velocity we can calculate the speed of the bullet. But it is really difficult to measure this H here, because for the 2 degrees, for example, this is the angle. So this is the angle that the pendulum is making with its initial position and its final position. So this angle will be extremely small. So for the small angles, so for example, we take that angle is 2 degrees. So for the 2 degrees, if we calculate this H here, so H is equal to, so L1 minus cos of theta, it will be 0.6 millimeter. So 0.6 millimeter is extremely small distance that it will cover in the y direction. So it is extremely difficult to measure the H here. So H here. So we cannot measure this H here. So what we can measure is this distance. So this distance is X. So if we measure the X here, so for example, for the 2 degrees, so I will not do the calculation for this one. This is the final relation that we get. So if we measure the X here, the X for the 2 degrees here, if the angle that it makes with its original position is 2 degrees, so we will get 3.5 centimeter. And 3.5 centimeter we can easily measure. So for that we have to measure the X. If we know the X, we can easily calculate the speed of the bullet. So for the small angles, so the H equals X squared divided by 2L, and so we can write equals 2GH equals GX squared. We just replace this with the H here. It's L. So the speed of the bullet that we get is mass, big mass. So we just put this value in this equation here. So we will get small m, so X, G, L, and then we get the speed of the bullet. So we do not need a very high sensitive instrument to calculate or to measure the speed of the bullet. So if we measure, so this is the function of X. So if we measure this distance here from the center of the mass and to the maximum position, this on the horizontal axis, then we can easily calculate the speed of the bullet. So the mass of the bullet we can easily measure. So the mass of the pendulum we can easily measure. G is a constant and L is a constant. L is the length of the pendulum. So we can easily calculate using using the conservation of energy and also the conservation of momentum. We can easily measure the speed of the bullet without using the modern high sensitive instruments.